We usually think of cameras requiring a lens and 2D sensor, but it's actually possible to reconstruct images using just a sensor and a piece of tape. Instead of a clear image focused using a lens, the modulated light on the sensor looks like a mess. I know it's hard to believe, but there's actually meaningful information in this measurement, and using computational algorithms, we can recover an image of the scene. This tape camera is an example from the field of lensless imaging, which consists of two types, coated apertures and meta lenses, which you may have heard of. They've been a really hot topic over the last decade or so. I'll be focusing on coated apertures by replicating the results from Laura Waller's diffuser cam paper that places a diffuser in front of a camera sensor. I picked this work because it captures many of the concepts in a demo that you can easily try out at home. And Dr. Waller's group has done an amazing job providing open source documentation and code to build your own diffuser cam using a Pi camera. All the links are below. Understanding how coated apertures work begins with what is called the point spread function of the optical system. For system engineers, we're talking about the impulse response. Imagine a single point of light at the distance of the object. Here I'm just back illuminating a piece of cardstock with a pinhole. The image of the point of light by the system is the point spread function. With a conventional lens, this appears like a single blurred spot. That size is limited by either aberration or diffraction. We'll now consider a monochrome 2D object, imaged by the camera. It's helpful to think of the object consisting of many individual points with varying brightness. To mathematically describe the formation of the object's image, we take the convolution of the point spread function with the object. If you're unfamiliar with convolution, you can't beat 3 blue, 1 brown's explanation and animation on the operation. Now, often 2D convolution is motivated by digital image processing. It explains how to manipulate digital images using all kinds of filters. The concepts are the same here, but we're talking about 2D convolution as a model for an optical system, the physical system itself. The reason convolution works as a model is because optical systems are typically linear shift invariant. In other words, the point spread function doesn't vary over the field of view, and the system response to each point can be added linearly. Okay, let's get back to the diffuser cam. Here I'm using a Raspberry Pi high-quality camera with a 3D printed mount to place the tape around 3 millimeters away from the sensor. This distance is important. The point spread function should appear focused on the sensor. Now, at first, I found it a bit odd to think of light being focused by a diffuser, but it's helpful to think of the surface having some average local curvature that results in the light being concentrated particularly well some distance from the diffuser. An example mentioned in the paper is the caustic pattern generated by a pool. An aperture mask of electrical tape then needs to be placed around the perimeter. The trade-off for how big this window is will become apparent a bit later. Now when we experimentally measure the point spread function using a point source, we get a pattern that takes up a large portion of the sensor, much different than a conventional, locally confined point spread function. Here's a little simulation to get an idea of how images are formed with the diffuser cam. If there are 2 points in the object, the result would be the convolution of the tape point spread function with these 2 points. What about 10 points? It's even more mixed up. Now let's take an actual photo of this little cat. It's a nightmare. We have light from every position of the object diffused over the sensor, overlapping and completely mixed up. There's no way a human could ever guess what the object is from the raw image. So is there some way we can undo the convolution to get an image of the scene? The simplest reconstruction is based on the convolution theorem. That is, convolution in one domain corresponds to multiplication in the Fourier domain. With this theorem alone, we already can attempt a reconstruction. Take the Fourier transform of the raw image, divide it by the Fourier transform of the point spread function, and then take the inverse Fourier transform of the result. But when we try this with the data collected with the diffuser cam, we get this result, pure noise. So why doesn't this work? The major problem is measurement noise. things like sensor readout and thermal noise, which usually have high spatial frequencies. And if the point spread function is close to 0 at any of these frequencies, the noise in the reconstruction blows up. But don't worry, we've got a solution for this, and it's called Wiener deconvolution. By adding this additional term, we can prevent the noise blowing up. Here, NSR is the noise to signal ratio. We are faced with the problem of knowing what the noise to signal ratio is, but we can take some estimates for this and adjust it to optimize the result. So let's try it out. We multiply the FFT of the raw data with this Wiener filter and take the inverse Fourier transform. And look at that, it's the cat. Adjust the NSR a bit and we can improve the reconstruction even more. Here's another scene viewed from the perspective of a smartphone placed in front of the diffuser cam. The raw image of the scene looks like complete rubbish like it did before, but it's not. Useful information is there, and we can make sense of it after the reconstruction. We can definitely see Oko text and maybe some faint letters from the canned air and the silhouette of the turtle. Now, Wiener deconvolution is a very basic reconstruction. One problem is that this approach assumes circular convolution. This usually isn't a big issue for a conventional point spread function because the wraparound artifacts are confined to just a few pixels near the border of the image. But for coded apertures, the point spread function is huge. What this means is that the reconstruction is only valid over a small region in the center of the sensor, specifically the pixels for which the point spread function still fully fits on the sensor. We could make the effective point spread function smaller by increasing the size of the border with electrical tape. This simplifies the inversion too, but it limits the resolution, so there's a complicated trade-off here. When I say inversion or inverse problem, I mean that we're trying to undo a forward operator from some measurement we acquired. Wiener deconvolution is just one way to address this kind of inverse problem, and it's not what's actually used in the diffuser cam publication. So even though it's satisfying to see something working quickly, the results aren't great, and what we can reconstruct is quite limited. A key idea to more sophisticated reconstructions is to express the inversion as an optimization problem, which looks a little different, maybe a bit more intimidating, than how the problem was expressed in this video. But this kind of framework really opens up a different way to think about image reconstruction. Well, if you've thought tape point spread functions are weird and interesting, there's a massive amount of related work beyond coded apertures, which may be more broadly referred to as point spread function engineering. I'll put some links below on other techniques with similar concepts. Next time, I'll go over solving inverse problems through optimization, try out different diffusers, and attempt 3D reconstructions. Special thanks to those supporting me on Patreon and the Waller Lab for their support and feedback on this video featuring their work. Stay tuned for more coded aperture imaging, and thanks for watching.